Okay, so let's talk through these two path integral examples that were a part of this activity. So the first one gives us a three-dimensional helical path, so this little spiral that starts at 3, 0, 0, and it spirals upward ending at 306 pi. And they give us the parameterization for that curve, so we don't have to come up with that ourselves. And they give us this vector field, 6x squared z, comma 3y squared, comma x. And we're supposed to find the path integral of that vector field along this helical path. And so to set this up in an explicit way, we need to find what is f of r of t. So we need to plug the vector field into plug the parameterized curve into the vector field to figure out as a function of t, what is this vector field doing at each point along this path. And so to do that, for our x's, we're going to substitute x of t, which is 3 cosine t. For our y's, we're going to substitute y of t, which is 3 sine t. And for our z, we're going to substitute z of t, which is equal to t. So we make all those substitutions. Then we need to find the dot product of that with a velocity vector to our tangent, to our curve. And so for the velocity vector, we'll just take the derivative of our parametric curve. So I'll get minus 3 sine t, 3 cosine t, comma 1. So when I take this dot product, I get some rather long and nasty expression involving cosines, sines, cosine squared, sine squared. So actually have an extra factor of t in here that came from this one right there. And so, as you might imagine, the next task of integrating this from t equals 0 to 6 pi is no picnic. So this one's just really tricky. Setup is everything, as usual. And so if you make it to here on a quiz problem or something like that, then I'm fine. Like the rest of what we do here, I wouldn't even want to do this one by hand. I don't have the patience for it. So I just pulled out a Sage calculator, and with the Sage calculator, I was able to figure out that this evaluates to 324 pi. So yeah, if you were daunted by this antiderivative, there is a good reason to have been daunted by this antiderivative. It's just a really nasty one. And so don't worry if you didn't make it to the finish line on that particular example. So the next one is a little bit more tractable to do by hand. So on this one, we're given a vector field in 2 dimensions, which is f of x and y is 0, comma x. So already this vector field is much easier formula-wise than the example that we just did. Except that now we're given a curve that has 2 parts, a semicircular part going from minus 2, 0 over to 2, 0 in the upper half plane, and then a straight line path from 2, 0 back to minus 2, 0 along the x-axis. And we need to find the integral around this entire closed loop. So we're finding a loop integral at the end of the day. But we have to do it in 2 parts. Right? So we have to first parameterize the top half of this circle of radius 2, for which we can use minus 2 cosine t, comma 2 sine t, t ranging from 0 to pi as our parameterization. How could we have gotten that? Well, I would have taken just the ordinary parameterization of a circle of radius 2, which is 2 cosine t, 2 sine t, and then just multiply the x-coordinate by minus 1 to just reverse it over the y-axis so that it runs clockwise instead of counterclockwise, and it begins at minus 2, 0 instead of beginning at 2, 0. So just like before, we have to evaluate the vector field on the parametric curve. So 0, comma x, but the role of x has to be played by x of t, which is the minus 2 cosine t in our parameterized curve. And so f of r of t is 0, comma minus 2 cosine t. And then we have a velocity vector, the derivative of our parameterized curve, 2 sine t, 2 cosine t. Dot product those two things together, and we end up with negative 4 cosine squared of t. And then we just have to integrate that from 0 to pi. Now, I didn't do out these details, so I hope that this is right. But to integrate cosine squared of t, we need to make one of those clever trigonometric substitutions where we can substitute instead of cosine squared of t, 1/2 of the quantity 1 plus the cosine of 2t is a substitution that we can make there, and then do a u substitution in that integral and go forward. And I think the integral evaluates out to 1/2. And if that's the case, then that integral is negative 4 times a half, which is negative 2. Then parameterizing the segment along the x-axis that runs from 2, 0 to minus 2, 0. We could have done this with our trick, our 1 minus t times the starting point plus t times the ending point, t ranging from 0 to 1. I chose to do it in just a slightly different way by parameterizing it as 2 minus t, comma 0, where t ranges from 0 to 4 over on this side. It turns out, as we're going to see in a moment, that it doesn't even really matter how we parameterize this. And the reason it doesn't matter how we parameterize this is if you look at the vector field arrows themselves along our path, the vector field 0, comma, x. It's this vector field that kind of looks like this. And then over on this side, it's like that. And so what do you already expect just based on that picture is going to be the value of this path integral?
Should be 0.
It should be 0 because we're traveling in a direction that is perpendicular to our vector field arrows at all times. And so let's verify, right? The vector field along the path, if I substitute 2 minus t in for x, f of r of t is that. My velocity vector is -1, comma 0. And so right there, oops, right there you can see that when I take that dot product, the dot product just ends up being 0 for all values of t. So if I integrate that from t equals 0 to t equals whatever, right? It doesn't matter where I integrate it, that integral is going to be 0. So that then the integral for my entire closed loop, c1 followed by c2, or what we would call c1 plus c2, is just going to be the sum of those two integrals, -2 plus 0, or -2. So that, I hope, is an accurate rendition of this integral. So the most important part of all this is, as always, the process, right? Getting the setup the way that you want it. So f of r of t dotted with r prime of t, and then integrating that between the limits of t that are appropriate for your curve. Today's examples, we had to work very hard and very explicitly to compute the values of these line integrals. In tomorrow's class, we're going to look at the case where our integrals are indeed path independent. And when our integrals are path independent, which isn't always, but when it is, we have a much more powerful tool to evaluate line integrals that much more closely resembles the ordinary fundamental theorem of calculus. In fact, it so closely resembles it that we end up calling it the fundamental theorem for line integrals, which is going to avoid us having to get into the weeds of having a parameterization and plugging the parameterization in and taking a dot product and yada, yada, yada. None of that will matter when our integrals are path independent because their value will depend only on the starting point and on the ending point and not on how we got from the starting point to the ending point. So when we meet the fundamental theorem of line integrals tomorrow, for those integrals to which it applies, it is a much more elegant, quick, and much less painful way to evaluate line integrals than the ones that we did here at the end of today's class.